Today, we're cracking open one of quantum computing's most promising algorithms, QAOA, and we're going straight to the heart of it to uncover the hidden engine that makes the whole thing work, the mixer. So picture this. You're trying to optimize a massive global supply chain. Or maybe you're designing a brand new life-saving drug. These aren't just tricky problems, they're insanely complex. You're hunting for one perfect answer in a sea of billions upon billions of possibilities. And when I say billions, that's an understatement. For a lot of these real-world problems, the number of options is literally bigger than the number of atoms in the known universe. So, yeah, your laptop isn't going to cut it. We need a whole new way of thinking about this. And that's exactly where QAOA, the quantum approximate optimization algorithm, steps in. It's this clever hybrid approach that's built to tackle these monster problems, not by checking every single option one by one, but by smartly exploring this huge universe of solutions to find the best one. So how in the world does it do that? Well, the secret sauce for QAOA is kind of like a two-part recipe. It uses two totally different tools, or Hamiltonians, that have to work together. One of them lays out the problem, and the other one? Well, that's the secret weapon we're here to talk about. Let's just think of this as a team of two. You've got the grader and the explorer. The grader, which is our cost Hamiltonian, is the expert. It knows the score for every single possible solution. And the explorer, our mixer Hamiltonian, is the one who actually does the work of moving around this universe of possibilities to find that top score. So the cost Hamiltonian, our grader, basically takes the entire problem and turns it into this huge, sprawling landscape. Think of it like a mountain range. The best solutions are the lowest, deepest valleys, and the worst solutions are the highest, rockiest peaks. The grader's only job is to create this map and label every single point with an elevation. Okay, but here's the million-dollar question, right? Having a perfect map is great, but if you can't actually take a single step, you're not going anywhere. If all we have is the grader, how do we actually explore this landscape? Well, let's just imagine for a second what happens if we don't have an explorer. We start out at some random point on our map. We then apply the grader, the cost Hamiltonian. And all that happens is the state gets a little twist, a change in its phase. But the actual probability of finding yourself at that spot, it doesn't change one bit. You're just spinning in place. You're completely and utterly stuck. So how do we get unstuck? Well, this is where some really cool quantum mechanics comes into play. To actually move, we need a second tool, a second operator, that doesn't play by the same rules as our grader. It needs to be able to push the system in a totally different direction, letting us hop from one potential solution to another. And that right there is the job of the mixer Hamiltonian. It is the engine of exploration. It's the piece that allows our quantum state to spread out into a superposition of many different solutions at once, letting it kind of peek at other parts of the landscape so it can start moving towards those deep, low-energy valleys we're looking for. Okay, so we have our explorer, but this is where things get really, really interesting. Turns out there isn't just one kind of mixer, and the type of mixer you pick actually defines how you explore the landscape. It's a fundamental part of your strategy. You can boil the mean strategies down to local versus global. The standard mixer, the transverse field one, does a local search. Think of it like walking around the landscape, step by step, just checking out the spots right next to you. But then you have the Grover mixer. It does a global search. This is way more like teleporting. It uses quantum interference to look at all the solutions at once and boost the good ones. So, which one's better? Well, the research is pretty clear. When you get to the really gnarly, complex problems, the ones with tons of interconnected parts, that local step-by-step mixer starts to struggle. Its performance just tanks. But the global Grover mixer, it holds up, maintaining its high performance no matter how complex the problem gets. And hey, don't just take my word for it. The researchers who studied this put it perfectly. They said the Grover mixer's global nature is exactly what allows it to effectively explore these incredibly complex energy landscapes, where a simple local search would just get lost. And this all brings us to the real heart of the issue. The dream of quantum advantage with QAOA isn't just about owning a quantum computer. It's about being smart, about designing the algorithm intelligently. And it turns out, the mixer is where all the action is. All right, let's tie this all together. The mixer is the engine that actually finds the solution. It's what keeps you from getting stuck in a dead end. And choosing between a local or a global mixer is a huge strategic decision you have to make.
Plus, for problems that have rules, like, say, a delivery route has to visit every city once, the mixer has to be smart enough to only explore valid answers.
So when you boil it all down, the single most important thing to remember is this. The mixer isn't just some random component you plug in, it is the search strategy. Choosing your mixer is choosing how you're going to attack the problem. And that leaves us with this huge, kind of exciting question for the future. As the problems we face as a society get exponentially harder, maybe the real frontier of quantum optimization is all about designing better and better mixers. Could building the perfect quantum explorer be the key that finally unlocks the solutions to problems we've always thought were completely unsolvable?